Okay, so number one. Okay. Anytime you see a natural log or log problem, we always want to consider expansion properties before we do derivatives, right? We would prefer not to do derivatives on such such problem with so many parts that we can separate. So we always want to try to expand first. So we can do that with 1, 2, and 3. All 3 can be expanded before we explore our derivative rules. Now our derivative rules, a lot easier. U prime over U for both these terms. The directions only say to expand, but we're just let's just make these all derivatives since we're gonna have to do that anyway. So yeah, for all these, we're going to also find the derivative after expanding, even though the instructions doesn't say to find the derivative. Okay, remember we talked about how if you have multiple terms multiplied and divided within a fraction, basically anything in the fraction will be expanded with a negative in front, and anything in the numerator will be part of a positive log term. U prime over u for each of these terms. We're on page 9. And 4 and 5 we're condensing, so we're trying to push all of the terms um, into one log term. So number 4, bring all the exponents up first. So push all the exponents up, or push all the coefficients up as exponents. Then we can put them all into one log term. So now we're just trying to put everything under one log term. We just have to find a home for the x to the 5th, y cubed, w to the 5th, and z to the 6th. So any positive terms will just go up top. Any of the negative terms will just go below. Everything is either getting multiplied or divided. Okay, number 5. Let's deal with this first. So the x minus 4 will go in the numerator since it's part of a positive natural log. The 7 minus x squared cubed and the 8 minus x will go in the denominator. And finally, that 1/5 that was here, we can push that up as an exponent. Okay. Number 6, we'll do what we did with 1, 2, and 3. Expand first and then derivative. Okay. Try 7 and 8. So 7 is just expanding like how we did with 1, 2, and 3. Number 8, though, okay, what derivative process do we have to make sure we involve with number 8? X cubed times natural log of x squared. We got to do what? Product rule, yeah. So number 7, we expand, rewrite the log expression as with rational exponents, bring that 5/2 down, continue expanding natural log of a over b as natural log of a minus natural log of b. As you do that, careful, remember that the 5/2 will distribute to both of the terms. And then you can do u prime over u. And keep the coefficients. Number 8, we have to go through product rule, f prime g plus f g prime. Don't have to clean up. I just showed the step, the cleanup step, but you don't have to. Okay, number 9. I'll walk through the steps with you, but for number 9 is log differentiation. The idea with log differentiation is that we are introducing logs into an equation that has no logs in it. Okay. We only want to do log differentiation if there's no logs at all in the equation. And the whole purpose is we want to take advantage of the log properties. So once we introduce logs into an equation, we can start separating all the different parts, all the different pieces. And the hope is that we can take one condensed problem, split them up into individual terms, and then the derivative will be a lot easier spread out across smaller problems. Okay, so here's number 9. It's a log differentiation. We'll take the natural log of both sides. Notice that there are no logs at all to begin with. But that right side, if we can introduce logs into the problem, we can start beginning our expansion process. Okay, so at this stage, we've expanded all the terms as much as we can. And now we have u prime over u for each of the terms. What's different is that we also do that derivative on this side as well. Notice that y is no longer by itself. It's inside the natural log function. So there's a little bit of implicit that happens here. So natural log of x is 1 over x. So natural log of y would be 1 over y. But because we're asking for y's derivative inside this expression, we got to keep track of our dy dx. There's only going to be one, though, since there's only one y variable. So this step, we begin our derivative process. Okay, we're pretty much done with our derivative process. The only thing left to do is to try to get that dy dx by itself. So we want to multiply or move that 1 over y to the other side. Dividing by a fraction is the same thing as multiplying by a reciprocal. So the y is going to come over to the right side. And as I do that, I'm also going to do a little bit of cleanup within my expression. The 20 over 2, I can make it 10 or negative 10. And our final step is, because we started with a function, our derivative should be able to be represented with no y variable. So that y is only a temporary variable. We'll replace the y back with the original problem. So we'll replace this y with this expression. So your derivative usually looks a little messier with log differentiation, but it's okay. You're not expected to do any common denominator and put it all back together. As long as you have all the pieces there, that's all we need. Okay, number 10, find dy dx. So the direction says use implicit, but we should be able to see the need for implicit without being told that this is implicit, because you see y's mixed into the equation here. So we know we have to involve implicit. But anytime we see a log or natural log, we always want to consider the possibility of expanding first, so that our derivative can feel a little bit easier, right? So the whole purpose of expansion is to make our derivative process easier. So we see natural log of xy. We prefer not to start the derivative process with the xy. Then we have to go through a product rule. That's a little messy within u prime over u. So I can use a product property to expand this into the sum of two natural logs. So now we can begin our process. We see two y variables, so we should be expecting two dy dx's. Just do a combination of either natural log rule or power rule for each of these terms. Natural log of y is just 1 over y. Thank you.
Thank you.
We need to include times dy dx. Two y's derivative is just 2. Now notice the y disappears, but we are asking for y's derivative, so we do need to include that times dy dx. So now we're just rearranging, right? Let's isolate the dy dx terms on the left side, factor the dy dx out, and then solve for our variable. Okay, we'll skip 11. 11 is just finding an inverse function. Let's look at finding the derivative of inverse at a point. This is where we create that chart and working our way around that chart. So let's look at number 12. Right, so this is our table here. We're always going to be starting at the bottom right corner. That's the unknown that we're looking for. Okay. We know 11 is the x value of my inverse, but therefore 11 must be the y value of my function. So I'm going to put the order pair information, the order pair relationship between my function and inverse in the top row. This is the derivative here. So I know that this must be true. Even without looking at the rest of the problem, I know that the 11 that I see is the y value of my function. So my first step is trying to figure out what is the x value of my function, because all my work is going to be done on the function side, because we're going to find the slope at whatever point, and then we'll use that slope value to make our conclusion of what our answer is going to be. Okay, so we can set 11 equal to our function. Bring everything over to one side. And this is not factorable, but we can use guess and check until we get to our answer for x. Okay, so It's going to be an easy number to find, a number that is close to 0, if not 0 itself. If 0 doesn't work, we'll try 1. If 1 doesn't work, we'll try -1. And we'll just keep going back and forth until we find our number. So I'll start with 0. Let's see, 0 in for x, -10 equals 0. That's not going to fit. Let's try 1. 2 minus 3 is -1 minus 10. That's not equal to 0. Try -1. So that's -2 plus 3 minus 10 is not equal to 0 either. Okay, moving on to 2. If I try 2, 2 times 2 cubed, that's 16. 16 minus 3 times 2, 16 minus 6 is 10. 10 minus 10 is 0, so that works. X equals 2. So we found our x value. Now that we have our x value, we can fill out our top row. My corresponding point. On my function side, there's an order pair 2, 11. On the inverse side, there must be an order pair 11, 2. So if I can find the slope of my f graph at 2, then this slope number will lead me to my answer. So to find f prime of 2, we first have to find f prime of x. To find f prime of x, we'll go through power rule. So the slope of my f graph at 2 has a steepness of 21, which must mean that on the inverse side, the corresponding point must have a slope of what? You guys remember? Yeah, 1 over 21. Yeah, don't change the sign, just flip the numerator and denominator. That's all we need. Okay, next page. Page 11, we'll start with 2. We'll skip the domain part. We'll skip 4 as well. We'll do 2, 3, and 5. And then page 12 will be your homework. I think we can get through the next 3 problems on page 11. Let's try that. So page 11, let's try 2, 3, and 5. Okay, number 3, y equals x raised to the square root of x plus 3. I want to make sure that we understand that this is not, first of all, it's not power rule. And also, this is not a to the u. A to the u rule would be something like y is equal to 4 to the x, or y equals 4 raised to the root of x. Notice the distinction here, right? This is a constant raised to a variable. This we can handle using a to the u, but this is a variable raised to the variable. We don't have a rule that can handle this. So we have to find a way to get this exponent to live elsewhere. And so this is another application of log differentiation. We want to introduce logs into the problem because that exponent is not in a place where we can apply a derivative rule as it stands. So take the natural log of both sides. Exponent can come down. Now, whenever you have a variable raised to a variable and you're doing log differentiation, you can always expect product rule to show up because that variable up in the exponent is going to come down. So now instead of a variable raised to a variable, it's going to be a variable times a variable. And that's going to cause us to always have to involve product rule. So we're able to bring that exponent down using power property. But now that we've expanded it as far out as we can, we do have a rule that can handle this, where before we were stuck not being able to identify a rule that can handle something in this form. So a little bit of implicit on the left side and then product rule on the right side. F prime, a little bit of chain rule here. So outside times inside's derivative. There's my F prime. There's my G. Back to F. G prime. Okay, so our derivative process is done. The only thing left to do is move that y over to the right side. And then remember, y is only a temporary variable. With log differentiation, we can replace our y back with our original x variable expression. I'm going to do some cleanup here within each of my fractions. Okay, let's do a final one here. Number 5, back to another derivative of inverse at a point. Same process as the number 12 from the earlier page. Zero doesn't work, one doesn't work, -1 doesn't work. Again, it ends up being 2. 2 cubed is 8. 2 times 2 squared. Sorry, 2. Yeah, so 8 plus 8 is 16. 16 minus 16 is 0, so 2 works. So f prime of 2 will lead me to a number that will help me get to my answer. So find f prime of x first. And find f prime of 2. My slope is 20, which must mean the derivative of the inverse at the corresponding point will be the reciprocal, 1/20. Okay, your homework is to finish up page 12. All right, come get your phones.